Hello and good anytime. Today in this lesson, we go study a very important electronic component called a transistor, where I will start with a very short introduction story. Now, during the beginning of the 20th century, when development began go on, at that time, the first ever computers produced were gigantic, like the size of a football field. Since the discovery of transistors, these devices now don't be very small in size in such a way that we fit carry them on our knees and even fit them in our palms like phones, tablet, or any other portable device. Today, because of transistors, processors that go offer much faster operation have been developed. Now, a transistor, now that electronic component or element wey go regulate the flow of current, voltage, and go even act as a switch or as an amplifier for electronic signals. This component be successfully be demonstrated on December 23rd, 1947 at Bell Lab in Morey Hill, New Jersey, in the United States of America. And since then, it has quickly replaced the vacuum tube that was used before as an electronic signal conditioner. Before we want to see this component, we go first see how it is composed as semiconductor devices through semiconductor materials. Transistors, semiconductor devices made of semiconductor materials. The characteristics of a semiconductor material differs between those of insulator and conductor. There exist three pure semiconductors elements, wey are the carbon, the germanium, and silicon. We get four materials that are used in industries today, which are conductors, insulators, semiconductors, and superconductors. Now, if we go back to the basis, elements with 3 electrons at their valence shell go make them a good conductor. Then elements with 5 or more electrons at their valence or outermost shell go make them a good insulator. And those elements with 4 electrons at their valence shell go make them a good semiconductor. Our ever first material wey we go see am na germanium. This material was discovered since back in 1886. Germanium lack of elasticity or flexibility or toughness na a fragile metalloid wey get a gray-white color. When germanium be reduced to a solid form or state, you go end up with a pure germanium. Then silicon. This material was discovered in 1823 before germanium. Silicon be found in the Earth's crust, that is, the outermost shell of a terrestrial planet, as silicon dioxide. They be white in color or sometimes colorless, and it be abundantly found in sand and quartz agates, and can be chemically reduced to a pure silicon in solid state, and not the most commonly used semiconductor material. Now, the big thing where we go look at here na the subatomic structure of a silicon atom. Since we be familiar with the valence shell, that is the outermost shell, here we get 4 electrons orbiting the nucleus of the valence shell. That is why na a good choice to use as a solid-state semiconductor material. In this particular case, we will talk about silicon atoms. Now we need to grow these silicon crystals, and this process be done in a perfectly clean environment where at the end of the process we go end up with pure silicon, that is intrinsic silicon. And when we grow it together as a crystal, we go develop what is called the covalent bonding. Covalent bonding na that process of sharing valence electrons, resulting in the formation of crystals. If we see at this structure, it is all laid out and like a geometric pattern. That is because that outermost valence shell is sharing the orbit with one next to it, and by doing so, we create this covalent bond. So therefore, the manufacturing process be very critical that all these have to be done in a very clean room. Semiconductors has negative temperature coefficient. Here, as the temperature dey increase, its resistance go decrease. One of the things wey you have to understand about these semiconductor materials na their behavior as it relates to temperature. So make you no be surprise say temperature does affect resistance and a conductor. But how this dey happen? So look, when the temperature increases, the resistance go increase. For example, when you get an extension cable cord wey dey hot or warm, na a very bad thing or symptom, because the hotter the extension cord, the more the resistance, and the cable cord go get more hotter, that will even cause fire. So that is the problem. Negative temperature coefficient is the opposite of as the temperature increases, the resistance go decrease. We fit say there is an inverse proportional relationship. That means it is a negative temperature coefficient. And this go be the behavior of our semiconductor materials. Now, with silicon, which is again the most popular semiconductor material, its resistance go be cut in half for every 6 degrees Celsius of raised in temperature. Meanwhile, for germanium, its resistance be cut in half for every 10 degrees Celsius of raised in temperature. Silicon be 1,000 times more resistive than germanium at room or normal temperature. Now why that? They be more stable. Germanium be used where heat-sensitive applications are necessary. Today, silicon be used for most solid-state applications and not really the big material that is used out there. Now why that? There is Silicon Valley. Where if you want visit Silicon Valley, it be located basically down in the San Jose area of California to the south of San Francisco. And now for they way a lot of the developmental work for the material silicon for electronic use will really take place. The conductivity in pure germanium and silicon. The electrical activity be highly dependent on temperature. Germanium and silicon crystals they function as insulator at low temperature. That is, at extremely low temperature, germanium and silicon will behave like insulators. So now, as the temperature go rise, they go start to acquire the characteristic of a conductor. For example, if we get a pure germanium and silicon material inside our text box, that's we just fix some box, we call and say a test box, where we fit control the temperature for inside that box. Now, by changing the temperature, go change the amount of resistance in the two materials where they inside that test box. Hole na a charge particle. The hole way I mean here na the absence of an electron will be hole. Now, how do we create an absence of an electron? The absence of an electron be created by the process called doping or ionization. So, for do this, if we apply energy into matter, we go knock out an electron off the valence shell. If we knock out an electron off the valence shell, that means we go left with a positive ion. And this positive ion means there is an absence of an electron. And the absence of an electron here in our discussion be signified as a hole. And the whole idea about this hole, let's say, it represents the loss of a negative charge. Therefore, it has the characteristic of a positively charged particle. Each corresponding electron and hole be referred to as an electron-hole pair. For example, now, if you be an electron, what do you want for do to fill a hole? And how do you want to fill this hole? By hanging out on the negative terminal as the holes are attracted